Hey everybody, so for projectile motion, you all collected data for your object rolling down the ramp. So let's say this is your ramp and you have some object rolling some distance d. Okay, first thing, how fast is it going here at the bottom of the ramp? Okay, so if you draw a free body diagram of your object, like this, there are two forces. There's the weight and the normal force, normal to this ramp. Okay, so that's done. Now let's pick coordinates. I'm going to pick my coordinates like this. So I put my x direction along the ramp, y normal to the ramp. I draw it a little straighter. And if we look at the geometry, this is horizontal, this is vertical. The angle's here, which is also here and here and here. Okay, so if I sum forces in the x and y directions, in the x direction, the x component of that, mg sine theta, the x component of the normal force is nothing, so then that's it. Equals mass times acceleration. Okay, y direction, I got the normal force and the y component of that equals mass times acceleration. Since our object is rolling only this way in the x direction, there's no motion this way, so ay is 0. There's only acceleration in the x direction this way. So I can solve for that. I can solve for ax. Okay, so I got the acceleration of the object as it's going down the ramp. Notice that this is constant. So we can use kinematics for constant acceleration. That's the one that looks like this. And for velocity, it looks like this. If you solve this for t and plug it in here and simplify, you get something like this. Okay. And if we start at rest, this is 0. This displacement is d. Our acceleration is right here. Okay, so if I substitute all that, I get 0 plus 2 this times d. Okay, and then I'll just square root. So there we go. We got the velocity at the bottom of the ramp. Okay, then this is on a table, and then your object kind of goes flying off the table and lands on the ground over here. Let's call this some distance, capital D, and I'll call this height h. And let's make an assumption that as your object goes from the ramp to the table, this becomes horizontal. The initial velocity as it launches off the table, let's assume that the magnitude of this is the same as the magnitude of this as it makes that transition. Like in my setup, I put that little piece of cardboard right here to make it kind of a smoother transition. And let's assume this is horizontal. If it's not, then it goes launching like this, which is okay, but by assuming it's horizontal, this projectile motion part of the problem becomes simpler, right? Because projectile motion, it's still kinematics for constant acceleration. Let me just rewrite that. Here's y. Okay, if I pick coordinates, let's say I'll make x this way and y this way. And get rid of all these extra marks over here. If I call this x and I call this y, then, right, if it launches like this at some angle, theta, that's fine. But if theta is 0 because it launches horizontally, v naught x would normally be v naught cosine theta, v naught y would be v naught sine theta. But if theta is 0, this becomes 1 and this becomes 0. So that's nice, right? So v naught x becomes 1, v naught y becomes 0. And gravity is this way, and I picked my y-axis this way, so ay right here becomes negative g. So let me put all those substitutions in there. Okay, so x, when it hits the ground, becomes d. And then I put my origin here, so x naught is 0. So this is 0. This is v naught, cosine of 0. And ax is 0. So that's all we have right here. Now here, when the object hits the ground, y is 0, because I put my origin here. So it hits the ground. This becomes 0. The initial height is h. That's 0. And ay is negative g. So we got 0 equals h minus 1/2 gt squared. Okay, so we got these two equations. So the faster it launches off the table, right, this number gets larger. And then if we want to solve for where does it land based on how fast it's going, let's solve for, let's see, where, oh, here. Okay, so this is the speed at the bottom of the ramp as a function of how high it was. And we can take that number and put it here, right? Okay, let's put everything together now. So let's just combine these three equations and let's figure out what is known and what is unknown. So that's the speed at the bottom of the ramp. What is a variable? The distance up the ramp. We're keeping the angle the same, gravity is the same. That's how far it lands on the ground. This, let's call these the same. That's this initial. This initial. The time it takes to land. The height above the table we're keeping constant. Okay, so all these unknowns. Let's see. What will be simplest? This entire. We can solve this for t and plug it in here. Or we can solve this for t and plug it in here. That's probably easier. So equation 3 for time, t would be 2h over g equals t squared, so square root. And I'll take that and plug it in right here. And also I'll take this from equation 1 and put it right here. So let me do that. So equation 2, d equals, I'll put time, I have it right here, so. And then this, which is also square root, so I'll just put it under the same square root. Okay, things cancel. 2 and 2 becomes 4, g over g. Okay, and notice, so this is the distance it lands is a function of how high above the table, how high up the ramp, and the angle of the ramp. And we're holding this constant and this constant. So really, how far it lands is only a function of how high up the ramp, which is what we were expecting. Right? This is the only thing that we were adjusting. And then this. And then if you look at it, the higher up the ramp, like this here, D, this one, the faster it goes here, and then the farther it flies and lands on the ground here. Because we're keeping this constant, we're keeping this constant, and gravity's constant. So what's weird is gravity factored out, so you can do this on any planet. And also what's weird is the time factored out. If you look at it, right here, the time it takes to fly through the air and land on the ground is a function of the height above the table and g. It's not a function of how high up the ramp, angle of the ramp, anything like that. So that's interesting. That means if you have your object, say here, kind of lower, then it goes down the ramp, flies off the table, lands on the ground. If you put it higher up the ramp, then it goes faster off the table, flies farther away, lands on the ground. But according to the equations, it's the same amount of time to land. So let's revisit the setup from last week where I had the toy trucks. The faster it goes, the farther it lands, right? Like the higher up the ramp you launch your object, the faster it goes at the bottom of the ramp, and then the faster it launches off the table, the farther away it lands on the ground. So this is zoomed in and slowed down. It takes the same amount of time to land on the ground. Okay, so I want you to plot one thing for this lab report. Plot the distance it lands versus the speed. So, right, this speed versus this distance. Other way around. This distance versus this speed. Meaning, on the horizontal axis, the speed, the vertical axis, the distance. Right, so this is meters. This speed is meters per second. And you did 5 different heights up the ramp, right? 5 of these. So you have 5 different speeds, and then they landed at 5 different distances away from the table. So you graph those 5. And then you do a trend line like this. Right, and then here's the equation for the trend line, slope-intercept form. That's the slope. What are the units for the slope? Slope is like rise over run, right? So like this divided by this. Like distance over speed. What are the units if you simplify that? Seconds. So that confirms what we were expecting, that here, the time it takes for an object to land is invariant. It doesn't matter how fast it was going when it launched off the table. That's what this confirms. If it's linear, it takes the same amount of time, and you can compare this slope, which is going to be the time, to what you expected theoretically, which is this. And then you can report on that in the lab report, and don't forget to show your graph in the lab report. And then that's pretty much it. So if you have any questions, let me know. Just post to the forum. Otherwise, I'll see you on the next video.